Hello, community. So great that you're back. We discovered AI's secret brain. We were all wrong about how AI really thinks. So, welcome to my channel Discover AI, where we look at the latest AI research paper. And I know that you will smile today all the way through. So, let's start. Holy cow, how is this possible that we finally figured this out? And you might say, but this is amazing. Absolutely agree with you. So, let's start. You know, in a classical vector space, like for example in RAG, we encode semantic similarity of our words or of our token. And now we have a brand new ArXiv preprint here that tells us that the reasoning process itself can have a better structural mathematical representation in a new mathematical vector space with a higher complexity that gives us a new representation that can be calculated much faster and much easier. We do have a better reasoning process. How did we achieve this? How was this possible? Now, let's start at the beginning. Okay, let's not celebrate, but let's start at the beginning. So the classical vector spaces from RAG, remember? Now, what they give us? They give us a map of concept. We calculated the cosine similarity of semantically similar vector embeddings. Now, this new preprint reveals that the LLMs can learn to build a far more sophisticated map of processes and relationship. So we don't go with conceptual items, but with complete processes. So this new map is much more complex and harder to create, but it offloads, if you want, the work of complex reasoning from a slow step-by-step calculation into a single fast lookup on the more complex map representation itself. What a beautiful idea! So, give you an example. Classical RAG semantic space organized into the whatness. A little bit strange, but never mind. So you have the question, hey, what is this text about? And you have a vector for King of France, and this is close to the French monarch, and this represents the concept as static points. This is the classical vector representation. And now we go to a geometric relational space, where the space is organized about how-ness. And it answers now the question, how do we get from point A to point C in a reasoning process? So this space does not just represent A and C as points in a mathematical vector space, but now it represents the path between them as a consistent geometric structure. So if you want, this path is now the logic complex reasoning structure as a geometry in a new abstract mathematical space. So this now suggests, and hold on to your socks, because that a key part of intelligent in this LLM, in this GPT model, isn't just the ability now to compute, but now that we understand that there is something going on in the way that memory is stored in AI, this would open up the ability to organize knowledge in complete new ways that makes future computation radically simpler, much easier, much faster. Hopefully a little bit cheaper. NVIDIA. So, what a gorgeous idea. So the reasoning complexity is now encoded in the relational memory complexity. It takes a little while to understand really what's going on, so I will give you some examples. So we effectively transformed the generic space into a specialized reasoning engine itself, where simpler geometrical operations, like finding here the nearest point or cosine similarities, are equivalent now to more complex logical deductions. So the pattern now create a geometry in a very particular mathematical space. Now, you remember here just my video yesterday where I was talking here about the end of AI, yes, beautifully. And what is really important to remember this particular moment where I was talking about the complexity sphere. This here is a sphere here, and we have here our data points, our knowledge point, and so ever. And we have here, if you want, a knowledge graph. And we can encode this knowledge graph, and we have machine learning for these encodings. And now it turns out that this encoding complexity, we can go to a high level. We can improve here the complexities that we can map in the graph structure to a process level. Examples are always good. Imagine you have to teach an AI about the cities in the world. You have two ways to do it. No? You have the flashcard methodology. This is what we have today. This is the associative memory. It just associates one thing with another, one dot with another. Paris is in France, or Lyon is in France, or whatever. And AI learns by memorizing this giant stock of cards. No? Great. Old-fashioned. New. Method 2, the mental map methodology. Now, yeah, I have to tell you, the first is a different training methodology. Now we do here that we do fine-tuning. We store here really the new information in really the tensor weights of our neural network. And now the AI draws a giant map inside its own memory. And you say, what? What is happening? How is this possible? So let's say it places here a dot for Paris, no? And because Lyon is also in France and it's geographically close, it places now the Lyon dot very near to the Paris dot. And it places now the Rome dot further away in a little different cluster that will later become Italy. So the AI doesn't just have facts now, it has relationships that it can encode. So for example, in this very simple simplification, the distance and direction between the dots mean something. And this is now what this ArXiv paper calls a geometric memory. And this is the very simplest idea, and this is happening in our neural networks. And we just found out today. Great. Geometric memory. Are you joking? Are you for real? Let's have a look. This is the paper. October 30, 2025, just before Halloween. This is from Carnegie Mellon University, Machine Learning Department. Beautiful. And Google Research, and Google Research. What a beautiful paper. And it says, hey, deep sequence models tend to memorize, and we are talking here about transformer architectures, but also about Mamba architectures. Get this. They tend to memorize geometrically, and it is unclear why. Isn't this amazing? Wow, we can learn something about it. So let's have a look. Careful. I'm not going to show you the mathematical details of this paper. This is a huge, massive paper with non-trivial mathematics. What I want to do, I just want to give you the introduction that you have the joy to read the paper personally, yourself. But I give you a little bit of a startup, a little bit of help at the beginning to explain the main concepts, the main idea, and the main insight, because then when you read the paper, you are not down in the mathematical nitty-gritty, but you can enjoy this, because this is really a nice paper. Example. A giant subway map of Rome, whatever you take. So you have a central station, an alpha station, and thousands of subway lines spread out like a star from this central node. Crucially, in this simple example, these lines never ever cross. And the puzzle is, I will tell you the very last stop of one of those lines, let's call it zebra 25 or zebra 250, and you must now tell me, as an AI, the first stop you would take from alpha to get there. So you see, we have to have a logical deductions. Now, if we go with this flashcard associative memory structure AI, it's almost impossible, no? It only has cards like zebra 25 is connected to Janky 24, and you would have to go backward and backward, one card at a time, backward and backward, and you go from this step to this step to this step, just to find the answer. And this is a very hard multi-step problem, and if you have 50,000 nodes, your AI will fail. I would say this is also looks like a chain of thought, as a reasoning pattern, but I'm not gonna tell you this. Otherwise, now for this new mental map AI with a geometric memory, this becomes now an easy task. Because on its internal map geometrical representation, all the stops on one line, you remember the lines never cross, are just clustered together in this mathematical space. So the dot for zebra 25 is now in a very specific location, in a subspace. And the AI just can ask, hey, which of alpha direct neighbors is in the same direction of the region as zebra 25 on my map? We have encoded the complexity of a multi-step problem going from card to card to card to card into the complexity of the space itself, into a new representation in this new mathematical space. And therefore it becomes a simple one-step lookup exercise. And this AI says, hey, that's simple, 1 millisecond or nanosecond. But hold on to your socks. They tested now a transformer on this puzzle on 2 different ways to provide external information and to start the learning process of this AI. And they go with in-context learning, and they go here with training from scratch and fine-tuning. And finally, I've been waiting for years for this particular paper because it finally explains the difference. You know, here we work with different activation scheme in our neural layers, and here we really have a change in the tensor weight structure of the layers itself. And this was all that we get until now, until this paper. So when you give here the AI the subway map here in a prompt in context learning here, you have a failure, no? This is the flashcard AI. I'd get confused, take some shortcuts and wouldn't solve the hard multi-step problem. Would just hallucinate something and it's gone. But when they train now, or particular trained an AI system on the map over time with this new methodology, letting it store the information in its own memory, so we have here now an update of the weight tensors itself, we have success. Almost 100% accuracy after the fine-tuning. Is this really possible that this is happening now because we have now a geometric memory structure encoded by the AI in the training process, by the training process itself? Is it that easy? Of course not if you watched here this video because you want to learn something and I want to learn something and I'm fascinated in context learning memory. Associative memory limited to local core occurrences explicitly given in the context, and for reasoning the model must compose the operation like the multi-hop traversals on the fly using our classical attention mechanism on the context token, but only modulate the, if you want, activation patterns in the layers. But this is fragile because without any persistent storage of this learning knowledge, the model cannot synthesize global relationship between non-adjacent entities unless they are repeatedly reinforced across examples. And what a coincidence that for my members of the channel, I have here this, as in 2 days ago, this video where I show you exactly new solution for AI agents that take care about this. But let's come back here to the main problem. This means we have now a statement that says, in context learning, in our prompt sequence, cannot synthesize global relationship in the learning process or in the reasoning process between non-adjacent entities. Holy cow! This is the explanation why ICL fails? Now, yesterday, if you remember, and if you have seen this video like you should, where I talked about the end of AI and some personal reflection, we were talking about complex n-dimensional spaces, where this here is the sphere here of a three-dimensional object, where we have here our knowledge graph that we are operating on the surface on this sphere. And then I told you there's the inner volume, and then we have lower subspaces, like these subspaces now are local subspaces. And now if I look at this sentence, I suddenly, and this is a really coincidence that I read the story, the ArXiv today, having done this yesterday, now I understand that this visualization of this subspace within a sphere, knowledge graph sphere, is not exactly this. It is missing here the global context, the global connex to the outer sphere with the global connection. It is not able to build here anything else than local connections in our reasoning chain, in our complexity patterns. Total different story within context learning memory structures. Knowledge is surprisingly encoded directly into the model parameter during the training, and this paper now argues that this leads to a geometric memory representation. Holy cow! Where the token embeddings are arranged such that their dot products encode global distances or relationship in the simplest case, even for entities, and now hold on to your socks, that never occur in the training data itself. So this means we encode now, how to say this, a reasoning capability in the structure of the space itself. Kind of breaks my brain. Let's go on. This contrasts now with purely associative memory. Yes, you know, where we have just local pairs, but not the global structure. So what is the key empirical difference that the authors found? And read the study. I just want to spoil you here. Just tell you, on the adversarial task like the POV star exercise, ICL completely fails. I showed you this. In distribution learning, the accuracy at the level here fails, while the in-weights with the fine-tuning achieves a near-perfect accuracy, even on a large graph if you have 50,000 nodes. to work with graph with 50,000 nodes and do here a link prediction or an edge prediction is not an easy, fast task. Until now. Now, if you are an expert, this is for you. If not, just skip the next 20 seconds. If you want to go a little bit deeper, the optimization barriers in context learning, it follows the wrong path. You have exponential time to the vast search space. In context learning has to explore this needle in a haystack problem. And simply, and the most important factor, lack of persistence, because the memory resets per prompt, preventing here the accumulation of global structure. So, okay, but let's look now at the benefit, the enabling factors in the in-weight learning procedure for the geometric knowledge. What is it? And now this is the most important information of this complete video. We have an L-fold composition into a one-step dot product query structure, given that we have now a particular graph structure, a path that clusters here in the embedding space, plus we have a spectral bias in the dynamics of the learning process itself, where, and I will explain this in a second, where the low frequency modes of a graph Laplacian, negative Laplacian, are prioritized over the higher frequencies. And this bias is the cause for this effect. And we end up with the parametric memory enables a one-step multi-hop reasoning, and the geometry pattern in the memory stems from the spectral bias of the graph Laplacian that arises naturally in the learning process. This is a correct statement, but at the beginning I said I don't understand anything. So let's go in and let's try to understand what it really means. There's something happening not because we force the system to limit the memory space or anything, because this has happened naturally. And this is the most important fact that is just amazing. That the AI learns a particular representation of the knowledge in a particular geometry. And these geometric patterns arise naturally because we do have a spectral bias in our neural network architecture, in the learning dynamic of our neural networks. And here we will go now to a simpler model, to a node to VAC, the simplest model, no transformer, no Mamba system, no nothing. And we will analyze this in an example, and then I will show you why this is happening. This is absolutely fascinating. But just let's focus here the formal explanation here. Why the disparity? ICL optimizes here for the local token prediction in isolation per context, which aligns, of course, poorly with global reasoning needs and traces. And the in-weight learning methodology of fine-tuning integrates now the supervision over many examples into our tensor weight structure, allowing here emergent properties like geometry to happen. And this is now something where I say, okay, I understand that there's no emergent property like intelligence happening, but now I understand that in this mathematical space an emergent property like geometry can happen. And this is fascinating. Now, just want to give you, if you go into the paper, there's you have to have some association with mathematics. It is not a simple paper to read. And therefore, I decided to make this kind of video where I explain everything to you. But if you really want to go here in the inner product here of the embedding vectors, then you can really enjoy here the mathematical formulation. It's a great study. Read it. So in summary, this means that for an in-context learning, my goodness, the activation patterns are not generating a geometric pattern in ICL. Only when we start the learning process of fine-tuning, modifying here the tensor weights here, the adaptation itself form now a new pattern in the memory when we have advanced reasoning patterns. Okay. I was going again over this. Again, why does it fail in context learning? Another, if you want, explanation. Why is fine-tuning with the in-weight learning happening? And now I switch over because the mathematics, I tried to explain it, but it gets too complicated too fast. So, you know what? I do an example. You are a sculptor. We are sculpting a block of marble and want to create Michelangelo's David. So, this is now the example I use here for fine-tuning here our in-weight tensor multiplication. So every single training example in supervised fine-tuning is a tiny tap with a chisel on our block of marble. Yeah? And then when the model sees now an edge A to B, this is a path. The gradient descent nudges now our weight vectors here for A and B to be a little bit closer together or related in a specific way. So if you want, if we are here on this block of marble, so we are, after millions of these tiny little chisels away, a coherent structure emerges now from the marble. So if you want, after this training process, we see the first geometric pattern or the map, the subway map. And this is not temporary. This is not limited to in-context learning, to the prompt sequence, to the context window, to token sequence, 1 million or 5 million tokens. It is a permanent feature that the system, the AI, the neural network, learned of the sculpture itself. The weights are now the coordinates of the points on the map or on the body here of David. The reasoning is now a structure, not a process anymore. You see, this is what we achieved with this new mathematical representation of a higher complexity into a vector space. The reasoning is now a structure itself, not anymore a linear sequence of step-by-step process augmentations, chain of thought. Why it succeeds is about the eigenvectors. So the fact that GPT learns these advanced reasoning patterns through simple supervised fine-tuning is what makes this discovery so profound. And I read the paper twice because I said there must be somewhere the reinforcement learning. Ne? There must be somewhere the reward model. There must be somewhere here the value function. There must be somewhere the advantages where we have here this adjustment by reinforcement learning. And you know what? Nothing. No reinforcement learning. The LLM is directly supervised at every single step to chisel away from the mama block here of the output. It's constantly being told, hey, I give you the right answer, no? Supervised fine-tuning, and it adjusts its way to get closer to the right answer. And this supervised fine-tuning, this simple process that we thought it's not really important anymore in the training of our LLMs, no? Achieves here a geometric memory representation. Wow. Now, to be a little bit more precise, the team here did not just, they started here with a pre-trained transform architecture. They started here from scratch. So they used here the training, the fine-tuning here from scratch. Typically implies supervised fine-tuning or pre-trained model here, llama, nothing. So they have their own from scratch training with the fine-tuning, with the supervised fine-tuning, no reinforcement learning. Amazing. You don't need reinforcement learning to have here higher complexity in your geometric reasoning memory? Hold on to your socks. That's all I tell you. The model isn't being rewarded for reasoning at all in this paper. No, it's just being trained to mimic here sequences, supervised fine-tuning. And the reasoning map in its all complexity, in all its glory, what we call the geometry, isn't something the model is trying to build consciously to maximize now a reward score, or like in reinforcement learning. Nothing at all. This geometry just emerges. But how? How is this possible? Can somebody please explain this to me? I mean, even more powerful. I mean, this is crazy, no? Just simple mimicry in the learning process. Supervised fine-tuning achieves a geometric representation pattern in the memory. Are you joking with me? Okay, so when forced into the high-dimensional space of neural network weights, this thing spontaneously organizes itself into a structure that enables advanced reasoning in the geometric pattern. Come on! I'm loving it. So, now what it does, this points here to a much deeper, it's the first day I read this paper, just some hours ago, to a deeper, more fundamental principle of how this GPT system and LLM models, transformer models, and Mamba models learn in general. And now it gets a little bit more challenging to understand, but I make it simple. I want everybody to have a big smile, because I'm going to tell you there's a mathematical explanation why it happens, and I'm not going to show you the mathematical explanation. I try to explain it in simple terms, and maybe I fail, maybe I oversimplify, but I just want to bring you the idea, you know, the core idea that you say, wow, what a beautiful idea. So let's stay with our block of marble. Yeah, the block is the random initial vector embeddings, and the goal is here to show here the shape of a person. The person is of course the graph true structure. Yeah? So what I told you about the spectral bias here. Now what is the bias? A sculpture doesn't start by carving out the eyelashes here of David. Nah? All those sculptures, they have a natural bias to start with the big fundamental shape of the body. The head, the torso, the limbs. Those are, in a mathematical parallel world, now the low-frequency compounds of the eigenvalues of this particular object that we call a statute. So only after the main structure is in place, our sculptor now chisel away the fine-grained, high-frequency eigenvalue details. Now you make the rough work and then you go on the details. Okay. Now the authors decided to go not with the complexity and start with the complexity of a transformer or Mamba architecture, but they go to a very simple neural network hundreds of thousands of years ago, Node 2X. I have dozens of videos on Node 2X. It's a training process, very simple, very similar to the sculptor. It's biased towards finding here the fundamental global shapes of the graph first, which means aligning its embedding with the low-frequency eigenvectors of the Laplacian. So if you want, this is the secret sauce here of all of this. This spectral bias is how an LLM trained on purely local information, your immediate neighbors, ends up creating a new representation that is rich with a global geometric structure. I would not have thought that I would say this sentence today, but wow. Yeah, if you're not familiar with Node 2X, here I explain what it is, Node 2X. That you see, it's just a simple toy neural network that makes it so much easier to understand. And they ought to stay here with Node 2X. They say the spectral bias refers here to the tendency of the LLM training dynamic process. Now, hold on to your socks to prioritize the low frequency. This means the global components of the graph spectral decomposition. And now, specifically aligning now the node embeddings of the graph with the top eigenvectors of the graph Laplacian matrix. This is the root cause. This is the core of why this happens naturally at the learning process of AI. This spectral bias emerges now during the optimization and local edge memorization task, leading now to new embeddings that capture now the global graph structure without explicit multi-hop supervision. Because we built the complexity into the geometry itself. We are not working anymore on a simple vector space of RAG. So this spectral bias is what drives this geometric emergence of the complexity of our neural network without any pressure from external that we say, hey, we will limit your memory, forget it. And you know what? We have even headroom for further improvements. The geometry arises naturally from the training dynamics alone. Linked to a spectral bias in simpler models here where the low-frequency eigenvectors of the gross Laplacian are prioritized. Now you might ask, why is this happening? Why is it that we have here a priority to the low-frequency eigenvectors? This is exactly what I showed you at the marble statute at David. You start with the big chunks. You start with the rough outline. You don't start with the eyelashes. This occurs independently of architecture capacity or supervisor constraint or whatever. And you know what? They even found that Node 2X produces a stronger geometric pattern than the transformer does. So we do have a further potential to optimize the reasoning process of transformer, trying to understand how the hell is this little Node 2X better than a transformer architecture in geometry. Geometric memory emerges here in the deep sequence models here of parametric storage here of the atomic quotation mark facts. It happens in transformers, in Mamba architectures. You find a global geometric representation in the embedding from the local co-occurrence supervision, supervised fine training alone. And this geometry encodes now the multi-hop relationship between all these entities, let's call it, via dot product, simple, you know this, cosine similarity from direct structure, enabling implicit in-wide reasoning on task, like pathfinding in graph with 50,000 nodes. Have you ever thought that this is possible, that a spectral bias can induce a geometric memory representation? I'm just amazed. And I think, hey, I hope you enjoyed it. This is the end. And then I thought, no, I have another example. I was trying to find simpler examples. Imagine your graph is not a drawing, or your graph is not David. Imagine your graph is a physical object, and we build here something like a neural network. So we have a lot of balls and a lot of edges connecting those balls that are the nodes here of the graph, and those edges are now rubber bands connecting all the balls. You know, you can imagine this. You have 20, 30, 50 balls, and you have a lot of rubber bands connecting all of them. And now imagine you go there and you lift some of the balls, 2, 3, 4, 5 balls up, and let the others stay low. So you see that you have with the rubber band, suddenly you have a tension in this geometric object. So what is the graph Laplacian if you're not into theoretical physics? Think of it as a machine that does a simple job. For any ball or any node in the graph that you pick up, it tells you how much tension it is under from its neighboring rubber bands. Of course, there's semantic similarity and complex reasoning patterns, but let's stay with rubber bands. So if you were to shake this network of balls and rubber bands a little bit in general, it would not just jiggle around randomly. It would settle into a certain vibrating mode in a very beautiful, pure pattern that we call in theoretical physics here, if you want, the mode of pure vibration. So it has an eigenfrequency, if you want. Yeah? And these pure vibration modes are here the eigenvectors here of the graph Laplacian. So you see, even a mechanic system will have this property. I hope this is an analogon to help you understand the complexity here. And here also we have the low frequency eigenvectors that are representative for the global pattern in our neural network. Imagine the entire left half of the network smoothly, you pick it up a little bit, you move it up, and the right half, you move it down, and then you will see here a beautiful swinging pattern. No? And it takes a long time here to complete one cycle. And this pattern here doesn't care about tiny little details. No? It reveals you the most fundamental structure of the complete graph, the major communities or the cluster structures here of this graph. This is the power of the prioritization of the low frequency eigenvectors that determine here the global pattern. And this is the reason why with the structural bias here, we have the emergence of a geometric pattern in the parametric knowledge. And then, of course, if you just go for single balls and you touch here a single ball and the next single ball and whatever, then you have a very fast jittery effect and you have very local patterns. Local patterns are noisy, we have local details. These are the eyelashes on the Statue of David, no? It's not smooth at all. You really go into deep into the nitty-gritty. You are now at the local level, the local pattern structure for explicit details. And you remember my video yesterday when I had here this idea? I'm sitting alone here as a little AI agent here in a classroom, and suddenly I get here the internet connectivity and I become from an LLM, I jump to an agent with a memory and external data. And I told you what's going to happen in the brain of an agent is that a world model is now synthesized. This means I have my parametric knowledge of an LLM from the pre-training, and I have an incoming external data stream that is not yet the knowledge. Just one day later, today, in this video, I can tell you that this parametric knowledge stored in the parametric memory enables us a one-step multi-hop reasoning process because of a geometric encoding. Amazing. Okay, here again, because if you have not seen it enough in this video, when the learning algorithm looks at the rulebook of smoothness, now our graph Laplacian for the network of facts, this is here the graph, it has a natural preference for learning the big, simple, slow vibration patterns first. It prioritizes here the low frequency eigenvectors. Chisel away the main chunks of the model block. And it does so because these patterns reveal the most important fundamental structure of the entire graph, the global structure, like its main community pattern, and so on. This is a natural process in AI learning, and I just can't say, holy cow! And this is exactly where I started this video. I hope you enjoyed it. I found it fascinating. I hope you enjoyed it a little bit. Hey, why not subscribe, become a member of the channel, and maybe I'll see you in my next video.